Hi, everybody from WCA Physics. Today we are looking at our lesson on friction. So comparing kinetic and static friction. And this one has some math involved, so I wanted to make sure I went through it with you, especially since we do not have live lesson coming up this week due to fall break. So I just definitely wanted to make sure that you had some support on this lesson. So it begins talking about a dog going down a slide. And the idea is that as the dog goes down the slide, the forces that kind of keep that dog on the slide are dependent upon a couple of different things. Depends upon the normal force acting on the dog. It also depends upon the amount of static friction acting on the dog. So we have to kind of look at and determine, oh, and also those are all dependent upon the angle of the slide as well, right? So we have to kind of determine some of these different factors here. So first of all, static friction. Static friction is the friction that a non-moving object has with the surface, and you have to overcome static friction to get that object to move. So that is noted by what we call the coefficient of static friction. And that coefficient can be measured, and we'll talk about how we measure that later. And what we can look at is if the coefficient of static friction is less than the force pulling the dog down the slide, which is a component of the weight of the dog, then the dog slides down. If the coefficient of static friction is greater than or equal to the weight of the dog, the component that's going down the slide, then the dog is going to stay where he is and not be able to slide down the slide. So we kind of break it down into this little picture here, and I'm going to draw that over here. So we have our slide. Try that again. Do this using my grid line so that's easier for me. Right, and on the slide is a dog. Gravity always is going to be perpendicular to the surface, to the earth. That's the weight of the dog. But the weight of the dog is not the part, like not the full weight acts down the slide, only part of it does. If we know this angle right here, which we're going to call theta, then we can kind of calculate these things. So the weight is going that way. The normal force is the part of the weight that acts opposite of the y component of gravity. So gravity or weight can be broken down into its x and y components. And we do have our normal force. Remember, that's the opposite of the y component of gravity. I can take this and I can drag this down here, and we can kind of see it as that y component of gravity. I'm going to just put it here because I want to should have made my arrow just a little shorter on that one. Okay. And then we have that component of the weight that's pulling the dog down the slide. That's what this is right there. Okay. That makes sense? That's the component. That's the component of the weight that is pulling the dog down the slide. We also have the component of the weight that's opposite the normal force. So we end up with a right triangle here. We have our right triangle. So when we get a right triangle, we know by triangles, since this is a little just geometry problem here, that this angle here is the same as theta. They're the same angle. That's just how those kind of work. We can look at, you break down the triangle, but that's how it works, right? So now we can use our laws of sine, cosine, tangent to determine our vector components. So this component here, which we're going to call the normal, here, we'll call this the normal force, right? So the normal force, the cosine of theta, this theta right here, is equal to adjacent, which is the normal force, divided by hypotenuse, which is the weight here of this triangle. So we can say that weight cosine theta is equal to the normal force. If we want the force that's actually pulling it down the slide, then we use sine, and we can do weight sine theta. Okay, and that's our gravity in the x direction that's pulling us down the slide. So we can see that on here. Basically, what we need is we need a definition of friction here. So friction is, or static friction, F sub S maximum here, is a measure of the normal force on the dog and the coefficient of friction. So friction depends upon, especially of a static friction, depends upon the mass of the object or the weight of the object. If an object weighs more, it has more friction with its surface. So we can measure friction, static friction, as mu times the normal force on the dog. It's dependent upon how hard that dog's pushing on the ramp, right? And we use the opposite here because it is pushing down, okay? So that's our definition of static friction. So static friction is pulling the dog up the ramp and, well, kind of, it's keeping the dog from moving, right? It's acting up the ramp. And then the x component of gravity here is acting down the ramp. So what we know is that these two, if they're equal, or if static friction is greater than that component, the dog can't go down the ramp because he'll be stuck. If this component here is greater than friction, then the dog will slide down. And that also depends upon the angle of the ramp. If I increase the angle of the ramp, then this is going to get bigger. This doesn't change. Well, it will change a little bit too, I suppose. It'll actually go down. But this part gets bigger, right? As well. So those components do change with the angle of the ramp as well. So that's also kind of important too. So as we go down here, that's kind of walking you through that stuff. We can see that we end up with this equation, which relates the coefficient of static friction to the angle. So they're going to walk you through a little bit of the math that the tangent of the angle is equal to sine of the angle divided by cosine of the angle. That's just a little trigonometry. And so we know that the coefficient of friction is going to be equal to the tangent of the critical angle. That's important. So when we go to our next slide here, it gives you some examples of this situation. If I have a bunch of different coefficient of frictions up here, static friction, non-moving friction. If I have a wooden object sitting on another wooden object, the coefficient of friction between the two of them is 0.62. But it also depends upon the angle, right? So if it's sitting on a horizontal surface, it's different. If it's at a vertical or more tippy surface, it's different. So we have to use this equation here. Coefficient of static friction, mu sub s is equal to the tangent of the critical angle, right? So let's kind of look at that example here. So here you say a block of oak wood placed on a clean, dry plank of oak wood remains at rest. Will it remain at rest if the plank is tipped at 35 degrees? Well, let's use this equation. The static coefficient friction is 0.62 between wood and wood. So the question is that greater than less than or equal to the tangent of 35 degrees, because that is the measure of the tippiness, right? So tangent of 35. So when I do the math, the tangent of 35 is 0.70. That is greater than the static friction coefficient. Since it's greater than that, I know that in this tug of war, that X component of gravity is going to win and the block is going to slide down. If 0.62 had been greater than the critical angle tangent, then it would not slide down, it would stay still. Okay? So then our next section deals with kinetic friction and how we determine static friction. So to measure static friction, what we do is we take an object called a spring scale, it looks like this, and we attach it to the object. And so there's a spring inside of here, and the more you stretch it, the harder you pull, this little dial is going to register at a higher force. It'll have a higher force, like a greater amount of newtons, right? So you can keep pulling and pulling and pulling on it up to a maximum point, and the maximum amount that you pull on it before it starts to move is considered our maximum kinetic or maximum static friction. That's what that is. On this particular graph down here, you can see that in action. Person is pulling on a block, pulling harder, harder, harder until it starts to move. And as it starts to move, then that drops off because the amount of friction in a moving object is less than in a stationary object. So now this object is starting to move, and as you get it to a constant velocity, the amount of kinetic friction will stabilize right here. So our maximum of static friction here was 12 newtons, and then it stabilized the kinetic friction at 9 newtons right here, right? So you can determine that coefficient of static friction by kind of using that formula we had from the first page here, this one right here, that the static friction is equal to the opposite of the coefficient of static friction times the normal, right? So this is the force it would take to move it, the maximum force it would take to move it. So let's look at this here. So the maximum force it would take to move it, we said, was 12. So we're just rearranging these variables to solve for that. Coefficient of friction static is equal to the force maximum divided by the normal. The normal force is dependent upon the weight of the brick. So the weight of the brick is 20 newtons. So the normal force or the maximum amount of force was 12. The weight of the brick was 20. And so the coefficient of static friction is 0.6 newtons, right? So that's how we determine that. We can determine the amount of coefficient of kinetic friction in a similar way. We're using this formula up here. We're going to solve here and take the force needed to maintain a constant velocity divided by the normal force. So that was 9 newtons. And the weight of the brick again was 20, so then our kinetic friction coefficient is 0.45. So that's where that all comes from there. All right, so that's pretty much it for all of the stuff in the friction lesson. If you have any questions, let me know. Otherwise, guys, I will see you in the next one and enjoy your long weekend.